Okay, I want to talk about the proof of this proposition 9.3.24, which is proving the laws of exponents for an arbitrary group. So be careful here. You can't assume properties of real numbers or integers. You have to use group properties only. So we're going to focus on part 2, and I'll say a little bit about part 3 later. Now, there were several cases here, depending on the sign of m and n. Some people used induction, but that proof only works when these are both positive. So you do need to separate into different cases. So I'm going to do one of the intermediate cases. This is actually one of the harder cases. So I'm going to prove the case where m is positive, or non-negative, and n is negative. Now, if n is negative, then minus n is positive. Okay? So you need to be careful here. When you see minus n in my proof, this is a positive number. Right? So what that means is that reduces this. Later on we'll see that when I have minus n, I treat that as a positive number. So I can cite one of the previous cases that uses exponent rules with positive numbers. So don't be fooled. When you see minus n, that refers to a positive number. All right, so let's go ahead and do that. Now, what we have here, g to the m to the nth power, remember this n is negative. So I should break this n up into a minus 1 and a positive power. This is the definition of a group element raised to a negative power. All right, so I have group element raised to a negative power is the inverse raised to a positive power. All right, so now I have a positive power on the outside, and I need to take care of what's going on in here. Now, here I have the inverse of a m-fold product of a group element. So let me investigate what is the inverse of an m-fold product of a group element. Well, g to the m inverse, it's the inverse of this product of g's, and that's equal to the product of the g inverses. And you can see that simply by multiplying these together. So let me just say that. You can check this by multiplication. How do you if you multiply this product of g's with this product of g inverses, the g's cancel one by one with the g inverses, and you get the identity. Okay, that's something to remember, that, and let me put that as a star up here, is g to the m inverse is equal to g inverse to the nth power. What this means is that the inverse of an nth power is the nth power of the inverses, just what I've written here. All right, so I have another way of writing what's in the parentheses here. G to the m inverse is actually g inverse m times. So what's the advantage of that? Well, now I have g inverse m times, and that's raised to the minus n. I can write g inverse m times as g inverse to the m to the minus n power. Now these are both positive, and we already proved the case where both powers were positive. So I can combine these two. Now again, this minus n is positive, so we're okay. All right, so that's g inverse to the minus mn. Now what can I do? Well, I'm actually going to use this very same proof here, that g inverse to a positive power, that's g to the mn. Now this is a negative number, so again, g to a negative power is the g inverse to the corresponding positive power. All right, so I've used this definition to go from here to here. So that completes the proof of this part 2. Okay, now let me say something about part 3. Part 3 actually builds off of part 2. It's not that much more difficult to do that once you have part 2. This says the nth power of a product is the minus nth power of the inverses in inverse order. All right, so to prove this inequality, it's good to start with the complicated side and simplify it down to the simple side. So I'm going to start with the complicated side, which is h inverse g inverse to the minus n power. Now, by 9.3.6, the h inverse g inverse is just the same thing as gh inverse. All right, so now I have gh inverse to another power. So this is a power to another power. This is exactly the case of part 2. Now, since I've proved these for all integers, I don't matter positive or negative integers, it still works. Here I have a negative integer. This minus n might be positive or negative. Doesn't matter. I can take gh to the minus 1 to the power minus n as gh to the power minus 1 times minus n, which is gh to the n. Okay? I can do minus 1 times minus n equal n because that's just regular integer multiplication. The exponents obey regular integer multiplication. So that takes the care of the proof of part